Our third paper this afternoon is by Qingping, and his paper is entitled Disinfection Efficacy Analysis of an Ultraviolet-C Device for Escalator Handrails. And this will be presented on video.
Hello, everyone. My name is Qingping Guo. I'm sorry I cannot attend this conference in person. This is recording my presentation. I will attend Q&A section, try to answer your questions. My presentation title is Disinfection Efficacy Analysis of Ultraviolet-C Device for Escalator Handrails. This is my presentation outline. COVID-19 and escalator handrail cleaning, UVC and UVC device we designed for escalator handrail. FEA analysis of the UVC device for UVC intensity, dose, and distribution on handrail surface. Disinfection efficacy test of the UVC device for 4 pathogens, 2 bacterial and 2 viruses. Some results and analysis. Final conclusions. COVID-19 pandemic requires a high hygiene standard for the public facility. Cleaning and disinfecting can reduce the risk of the infection. Dracker EHC is the world leader of the handrail manufacturing. Handrails are widely used in the public place. Disinfection of the handrail surfaces is our responsibility. UVC has been recognized an effective method for a long time. We cooperated with the UVC LED company to design the UVC device for disinfection of the handrail surface. In this paper, we focus on the analysis of the UVC device by using FEA method and disinfection efficacy test, then to show how powerful the UVC device. This slide shows the assembly position of the UVC device and handrail. The UVC device was fixed inside of the escalator system and cannot be seen from outside. This device had 4 UVC LEDs. LED, not like before the mercury vapor discharge lamp. LED has some more advantages, such as no mercury, no long time heat up, and small size. Based on this structure of the UVC device, the handrail top surface will receive more UVC than 2 sides during the handrail passing the UVC device. This is why we designed the reflectors on the 2 sides to enhance UVC for size of the handrail. In order to make sure all analysis of the UVC device are reliable, in this paper, we use FEA method to analyze the UVC device parameters. The simulation software is control multiphysics. We use the compression method. First, left side on the slide shows the result measured by using the commercial UVC meter. We measure 2 positions with the various distance UVC intensity. One is the center position and one is the side position. Dark red line means the center position value, and the blue line is for side position value. Left side on slide shows the result simulated by the software and exactly setting up the parameter during the measurement. Left top shows the 2 positions. Based on the 2 results, the trends are exactly the same. However, the absolute value is not the same. Using mathematical method, the relationship between the real value and the simulated values were established. That's the simulated value times 3 equal the real values. After we corrected the simulation results by using measurement results, simulation will be used to get the precise UVC parameters, such as intensity, dose, and distribution at any point. This slide shows some simulation intensity results. First, the UVC intensity has a significant difference with the different distance. The shorter distance, the stronger intensity, and the narrow distribution. It is well known the UVC disinfection efficacy is proportional to the UVC dose. The dose value and distribution is very important. Based on the simulated intensity using integration method, the dose received by handrail surface can be calculated. Due to the curved surface of the handrail, the UVC intensity and distribution are different. Each point received dose is different. In order to know the dose on the surface, we mark the allowed parallel line on the surface, like left side on the slide. Each line received the same dose. Diagram on the slide right side shows the calculated dose received on the surface with different distance. By comparing the results, we can see no significant difference with various distance. That's because closer distance with higher intensity but narrow the distribution. So the integration didn't show significant difference. The two sides on the surface receive less UVC dose. Based on this result, the distance 8 to 10 millimeters is recommended for the assembly of the UVC device to handrail top surface. After analysis of the UVC device using FEA method, we know exactly parameters of the UVC on the handrail surface. Next step is to test the disinfection performance of the UVC device for the pathogens. This work is cooperated with Professor Ben Hatton team of University of Toronto. We test the two bacteria and two viruses. Due to the UVC device size, the UVC only can scan very narrow band area. The scan time is dependent on the running speed of the handrail. Actually, after UVC device scans the one area, it will wait one cycle to scan the same area again. Typically, the handrail one cycle needs 1 minute. This flow chart shows all the tests were conducted under two modes, continuous and pause cyclic. Continuous mode is easily understood not stop after UVC LED turn on. The pause cyclic mode means UVC LED turn on 0.1 second and then turn off 1 minute to finish one cycle. Pause cyclic mode can be done many times until accumulated time equals total exposure time. For comparison purpose, we will keep the same total exposure time for continuous and pause cyclic mode. This slide shows the test background. I want to emphasize the pause cyclic mode is to mimic the handrail running condition. When we test, all the test samples were put in the middle red area. That will be easily for us to know how much dose received by the passenger during the test. After finishing all the tests, we compare the result between the continuous and the pause cyclic test based on the test result for the bacterial E. coli. In Figure A, under the continuous test, the disinfection efficacy was higher than under pause cyclic test. We found that the reason is the sample number was different for both tests. For the paused cyclic test, the sample number was less. Figure B showed the disinfection efficacy was increased when the test sample number increased. In order to fairly compare for the both test result, in Figure C, we use the interpolation method to obtain disinfection efficacy value at the same sample number. Figure D shows the comparison result after we correcting the result of the paused cyclic test. It shows the disinfection efficacy didn't show significant difference for continuous and paused cyclic tests. This slide shows some test results using UVC device for 4 pathogens. For comparison purpose, based on the test result, we calculated D99 for each pathogen. D99 means dose can inactivate 99% of pathogens. Based on D99 for each pathogen and the UVC dose handrail top surface received in each cycle, the cyclic number needed to inactivate 99% of pathogens can be calculated. The slide shows for the running handrail how many cycles are needed to inactivate 99% pathogens. This is the conclusion of this paper. The first is the UVC distribution, intensity, and dose of the UVC device on the escalator handrail surface was accurately analyzed by the combination of the measurement and the FEA simulation method. The second is after analyzing the test result for the E. coli bacterial, the disinfection efficacy of the pulse cyclic test and the equivalent of the continuous test didn't show a significant difference. Last is the D99 for the 4 pathogens was obtained based on the test results. The times required to inactivate 99% of the pathogens on the handrail surface are obtained. Thank you. Any questions?